The Autonomous Operating System, the AOS, model-based plug-and-play autonomy for robots in partially observable probabilistic domains with noisy sensing, a research of overtime and Dan Suissa under the supervision of Professor Ronen Brafman. Motivation. An increasingly wide range of robot skills is currently available. How can an autonomous robot use them to perform tasks? The current state of the art is to use handwritten scripts or state machines to schedule skills into effective behaviors. The challenge is that scripts or state machines are non-optimal, how to maintain upon environment change or robot skill upgrade. The solution is to use AI planning algorithms to control the robot. The problem is it requires AI expert and a significant integration effort. Our goal is to provide plug-and-play task-level autonomy for robotics. Our solution, the Autonomous Operating System, the AOS, which offers several advantages. Conceptually, we provide full POMDP support with stochastic actions, partial informations, noisy sensing, complex goal, and optimized behavior while balancing trade-offs. We offer an abstraction mapping, which is an explicit and principled mapping between the skill model and skill code. We use generative POMDP models that are based on probabilistic programming language constructs. It offers greater expressive power, easier to specify, and enables much faster sampling rates. Generically, we provide a true plug-and-play system. Given properly documented skill code, no additional programming effort is needed. Documented skills can be added incrementally and used by the system. The AOS uses reinforcement learning to auto-generate MDP heuristics of POMDP solvers. The system has a GUI to visualize the robot belief state distribution and understand the robot's behavior. So how to use the AOS to develop autonomous robots? We will overview a simple, fully observable deterministic example of a robot playing tic-tac-toe versus a human. To implement this example, we need the robot to be able to draw a circle in each of the cells and detect the new state after the human's turn. Implementing robot skills is out of the system's scope, so we assume the skills were implemented. The next step is documentation. We start with the environment file called df to specify skill-independent aspects of the model. These include general POMDP parameters, state variables, terminal state, state-dependent rewards, and extrinsic events. Below is the tic-tac-toe EF file. On the left, we see the general POMDP parameters, such as the action look-ahead horizon and the POMDP discount factor. Next, we define the state variables. In tic-tac-toe, it is only the grid cells and whose turn it is. Beyond the C++ primitive types, users can define compound types or enums, as we did in this example. On the right, we see the reward code, which describes terminal states, and state-dependent rewards. We specified rewards for winning, losing, or time. Finally, users can define extrinsic changes not invoked by the user. We define the human player's behavior as uniformly marking an empty cell. It is not the best policy, but enough for this example. As you can see, the domain specification is compact, flexible, and hence easier to understand for engineers. Notice the use of generative code model. We only describe how to sample from the extrinsic change in distribution. Conceptually, we are moving from declarative to generative models. The next step is to document the skills. There are two files, the SD and the AM file. The SD file is shown on the left. Semantically, it specifies a fragment of a POMDP model associated with a specific action or skill. It describes the expected high-level impact of applying the skill, how state variable values change, the associated reward or cost of the skill, and the information the skill supplies. In the POMDP model, these are called the transition reward and observation models. Detect does not impact the world, so there is no transition model. The reward model is simple. The skill does not have a cost, only a soft precondition that detect should not be applied on the robot's turn, with a penalty of -10. The domain is fully observable, so the observation is a string, a mapping of the board state. On the right, we see the detect AM file. It connects the more abstract model of the skill with the skill code. It specifies how to activate the skill code, the detect tic-tac-toe raw service in this case, and how to translate the skill code execution to an observation corresponding to the model. Local variables store events that occur during code execution, and in this case, the observation is the OBSR local variable that stores the return value of the skill code. We now describe the draw skill documentation. On the left is the SD. In POMDP terms, an SD file describes an action template. The skill receives a cell position parameter, and there is one concrete POMDP action for every possible position. The possible values of a skill parameters are described in the available parameters section, an array of tuples that contains the possible context of a skill activation. Cell position can be from 0 to 8 here. The precondition is not to activate the skill in the human's turn and only to mark empty cells. In the dynamic model, we define that the given cell is now O, given it was empty, and the observation is always success. So this is a simple deterministic action. The AM file on the right plays a similar role as the detect AM file. It works well, but was the effort justified? We see the gain when things change. Suppose the robot is now faulty and marks the center cell only half the times. If it fails, the turn passes to the human player. Changing a script is not trivial, even for this simple change. Or what if we want the same skills for a different objective? The new task goal is to mark cells adjacent to a corner cell with the player symbol. Adapting a script or a state machine to play this game is non-trivial. In the AOS, the changes are minor and easily done. For the faulty arm, we just define a Bernoulli distribution for succeeding in marking the center cell and a possible failure observation, which should be added to the AM file. For the new task, we just change the AM file reward model. To conclude, we will see how the AOS solves the toy collection domain, which is a full POMDP. A robot receives a reward for bringing toys to a child. The toys' locations and values are unknown to the robot, yet some prior knowledge is given for the initial belief. The robot has a navigation skill that may fail and has a noisy report for its success. The pick skill can only be used 6 times, and it only works if the robot is near the exact toy it tries to pick, yet it receives an accurate observation of the pick's success. This example emphasizes the advantage of using POMDPs. See how actions are selected based on the belief state distribution rather than a single possible state. When the belief state is visualized, we can see the reason in the robot action selection. See how applying probabilistic actions like navigation adds uncertainty, and how observations focus the belief based on their accuracy. The failed or successful pick observations supply valuable information that reduces uncertainty and assists in decision making.